How on earth do engineers perfect the design of something like a jet engine or a Formula One car before they even build a prototype? Well, they do it by simulating things we can't even see, the flow of air, the movement of heat. But here's the real question. How do they know if the computer simulation is actually right? That's what this is all about, and the answer is hidden in the world of computational fluid dynamics.
I mean, think about it. Building physical models is crazy expensive and takes forever. What if you could just run thousands of tests in a virtual wind tunnel, tweak the design a little bit, run it again, see what happens? That's exactly where CFD comes in.
And this isn't just for fast cars and planes. The applications are huge. We're talking about predicting the lift on an airplane wing, how a massive ship cuts through the water, what's happening inside a roaring engine, and even something as delicate as how blood flows through our own arteries. It's a tool for understanding physics at every scale.
So what's the official definition? Well, it's the analysis of systems with fluid flow and heat transfer, using computers. Basically, it's a way to take really complex physics equations and turn them into visual predictions that we can actually use to build better stuff.
But how does a program like this actually work? It's not a magic black box. There's a very clear, very logical process happening under the hood. So let's pop it open and take a look. Pretty much every CFD job boils down to three main parts. First, you have the preprocessor. That's where you tell the computer what you're studying, the car, the artery, and you chop it up into a grid of tiny little pieces. Then at the very end, you have the post-processor, where you get to see all the cool, colorful results. But the real workhorse, the heart of the whole operation, is that step in the middle, the solver.
Yep, the solver is the computational engine. It takes the problem you set up and just crunches the numbers. It applies the fundamental laws of physics to every single one of those tiny cells you created. This is where all the heavy lifting happens.
Now here's the thing. The physics involved here is so complicated that the solver can't just spit out the answer in one go. It's not that simple. It has to work its way towards the solution.
So instead of solving it directly, it uses what's called an iterative process. You can think of it like a super smart version of guess and check. It makes an initial guess for how the fluid is flowing, then it checks how wrong that guess was, and it uses that wrongness to make a slightly better guess. And it does this again and again and again, maybe thousands of times.
Which, of course, leads to the million-dollar question, right? If the computer is just guessing and getting closer and closer, how does it know when it's close enough? How does it know when to stop? Because if it stops too early, your results are junk. But if you let it run forever, it's totally useless. It needs a signal.
And that signal, that critical piece of the puzzle, is something called a residual. Honestly, this is the key. If you understand residuals, you can understand how to trust a CFD simulation.
So what in the world is a residual? In the simplest terms, it's an error score. For every single guess the solver makes, it calculates a residual to see how well the guess actually satisfies the laws of physics. A high residual means, nope, bad guess. A really low residual means, okay, we're getting warm, this is a good guess.
To get just a little more technical, what the solver is trying to do is balance an equation. It wants to make the left side equal the right side. The residual is literally the difference between the two sides. It's the imbalance. The whole point of the simulation is to drive that difference, that error, as close to zero as it can possibly get.
This is why engineers don't just hit run, go get a coffee, and blindly trust whatever picture comes out. They are actively watching these residuals the whole time. It's a process called a convergence test.
We say that a solution has converged when those error scores, the residuals, have dropped down to some really tiny number. It's the signal that the guess and check process is pretty much done. The imbalances are negligible, and the solution itself, the pressures, the velocities, the stuff we actually care about, has settled down and isn't really changing anymore.
And this plot right here, this is the money shot. This is what an engineer wants to see. Along the bottom, you have the number of iterations, so the number of guesses. And on the side, you have the error, the residual. Each of those colored lines is a different physics equation. And you see how they're all trending down and to the right? That is perfect. That means with every guess, our error is getting smaller. If those lines were flat or worse going up, yeah, that's a huge red flag that something is wrong.
So how low is low enough? Well, it depends, but a very common target for that error is to get it below 10 to the minus 5. That's 0.00001. We're talking about an error of 1 in 100,000. When things get that small, you can be pretty confident that you found a stable, reliable answer.
So let's zoom out for a second. Why does all this technical talk about residuals and convergence really matter in the big picture? It's all about one thing.
And that one thing is trust.
A converged solution is a trustworthy solution, period. Watching the residuals is how an engineer confirms the solver did its job right. Without checking these plots, all those beautiful, colorful images of airflow could be completely meaningless fiction.
And this really gets at the fundamental trade-off here. On one side, you have perfect accuracy. We could try to force the residuals to absolute zero, but that would take a nearly infinite amount of computer time. It's just not practical. On the other side, you have engineering accuracy. This is the sweet spot. We push the error below a tiny, acceptable level, and in return we get a reliable answer in a reasonable amount of time. That's the real goal.
And that leaves us with this final thought, doesn't it? In this whole complex world of simulation, the computer can tell us the error, but it can't tell us when to stop. It's the engineer who has to decide where that line is between perfect and practical. It's a fascinating dance between pure computation and ultimately human judgment.